Everyone. This is section 4.9 for Algebra 2. And this covers what's called the graph standardization theorem, although I'll be entirely honest, you'll probably never hear me use that word again. Realistically, what this lesson is all about is taking the two things that we've been working on for the last couple of days. So we started with size changes in lesson 4.7, and then we did translations in lessons 4.8. We're going to be doing those at the same time to a graph. So there's really not a ton of new information that I'm going to teach you today. It's really more how do you work with these things at the same time? Okay, how do you put them together? So I've started you off with an example here of both a size change and a translation. And we're going to talk about what are all of those things going to do to this graph of y equals cosine of x. Okay, so looking at it piece by piece, I first just want to identify what is each one of these things going to change about my graph. Okay, so this 2x, that's a horizontal stretch. And when I do horizontal stretches and shrinks, what that's really doing is changing the period of my function. Okay, so down here I'm going to just make a note that the 2x is going to take my period and double it. So the new period of my function will be 4 pi instead of what it was originally, which was 2 pi. Okay. When I'm looking at size changes and I'm looking at what's going on with the y, that's really a vertical stretch or a vertical shrink. That's going to be affecting the amplitude of my graph. So when I have that y over 2, that's taking my amplitude, which was originally a 1, and dividing it by 2. Okay, so it really just becomes a 1/2. My original amplitude is 1 and it's getting cut in half, so my new amplitude is 1/2. Then we look at our translation over here. And remember that the horizontal translation, which is the thing with the x, gets its own fancy name. That's what's called a phase shift. So where I see the x plus pi, that's going to give me a phase shift of, let's see, what was it, pi units to the right because it's positive. Okay. And then the y minus 4, anything going on with the y is going to be dealing with a vertical change of some kind. So this would be a vertical shift. So y minus 4 is giving my graph a vertical shift of 4 units down. Okay, so that's how all 4 of those things are going to kind of work together. Each one of those things affects one property of my graph. So when we go to apply this to our graph of cosine x, we really have to pay attention to what order we put the things into the equation. And anytime we're working with equations of any kind, everything is backwards from what you would think it would be. So we're used to that, right? We're used to, like, for example, when it says plus, we do a minus and things like that. But we're also going to put the stuff into an equation in a way that's maybe opposite of what you would normally think. So with order of operations, typically we would do our multiplication stuff first, and then we would do our addition and subtraction. But when we're building the equation, everything kind of happens in reverse. So we're actually going to do this stuff first. And so you might want to make a note to yourself, and I'm just going to kind of do this off to the side here, that when we're writing equations, we're going to apply the translation before the size change, okay, when writing an equation. And it's important that you make a note that that's when you're writing an equation, because there's going to be some other stuff we do where that doesn't necessarily apply. But if it has to do with writing the equation, everything is backwards. So when I go to write my equation for y equals cosine x, the first thing I'm going to do is put in my phase shift and my vertical shift. So I'm going to start with y equals cosine of, and I'm going to write it as x minus pi, because remember it's backwards. And then that minus 4 would really go over here with the y as a plus 4, but then I'm going to swing it over here to the other side and make it a -4 again. Okay, so that's with just the translation. Now I'm going to apply the size change to that, or the scale change. So I'm really doing this. So I want to take that 2x, and really I'm applying it to my x value, but it's already got the pi with it. So I'm going to write it as cosine of x minus pi, and that whole thing divided by 2. And then for my amplitude, I really want to take that y and double it, right? So I'd be putting a 2 over here with the y. But if I swung it back over to this other side, it would become a 1/2. Okay? So this is what my final equation looks like. 1/2 cosine of x minus pi divided by 2. Okay? And this would reflect all of these things that we pointed out. So let's take a look at that real quick. But what I've done here is I went ahead and graphed the original parent function, y equals cosine of x, and then I graphed the equation that we just came up with a second ago in that first example, because I wanted you to be able to look at it and see what's actually happening. So the blue line is the parent function, the purple line is our new graph, and I want to be able to verify that what we said is true is actually true. So in your notes, if you look at what you just wrote down, the period changed from 2 pi to 4 pi. So if I'm looking at the blue line, if I go from 0 to 2 pi, I've completed one complete cycle. Okay? Whereas when I'm looking at the purple line, I have to go from 0 all the way over to 4 pi here to complete one full cycle. Okay? And you'll see that it's kind of squashed there. It's a real flat looking curve. There's a reason for that too. We'll talk about that actually right now. Because next up is the amplitude should be 1/2. All right. So if you kind of envision this as being the new center line, and I actually did this here to make that real obvious. So that black line there that just popped up, this right here, is kind of your new center line. And that came from the fact that we did a vertical shift of -4. But if you look at the distance above and below that black line, it should be a distance of 1/2. We could zoom it in and check for sure, but that should be a distance of 1/2 because we said our amplitude was going to be 1/2. We took our cosine curve and shifted it by a value of pi. So this point right here would typically be right on the y-axis, right? The top of a cosine curve is typically, the y-intercept there is 1. It typically starts right on the y-axis. We took that value and we shifted it over by a factor of pi. That's how we ended up with this point right here. Okay, so it got shifted to the right by a factor of pi. And then, like I already mentioned, we took this whole graph and dragged it down by a factor of 4. Okay, so that's how the equation kind of relates to all of those different things. And we should be able to go both ways. If I tell you what's happening to the graph, you should be able to come up with an equation. If I give you a picture of the graph, you should be able to figure out what happened and then write an equation. Okay, so let's go back to that next example, see if we can get through at least that on this, at least this first video. So under example 1 here, once again, I've given you 2 different transformations. I want to apply them to the equation, and then I want to identify each of these things. And then again, I'll probably go back to the graph and verify that that actually happened. So when I apply the transformations, remember this note we wrote to ourselves up here, that we are going to apply the translation before we apply the size change. So first thing I would do is make this y equals sine of x plus 3 pi over 2 with a +1 hanging out on the outside, okay? Because we do the opposite of whatever is going on in my rule, but remember for those y values, it would be the opposite over here, and then when you move it, it would turn back to a +1. So this right here would reflect just these 2 things. And then we want to take these values and add them in there. So when I see 3 times x, I actually want to take this thing and divide it by 3. I could also think of it as multiplying by 1/3. That might be an easier way to write it in here. I want to do 1/3 times this whole thing, everything that's there with the x already. And then I also want to take that y and multiply by 5, okay, which I'm going to move to the other side in just a second. So that's me applying the size change rule. So when I rewrite it nicely, If I move the 5 to the other side, it's actually going to be a 1/5 sine of, and two ways you could write this. So you could write it as 1/3 times x plus 3 pi over 2. Or we could write it as this whole thing divided by 3, just like we did up here. Okay, I just didn't have the room to divide by 3, but I thought I could squeeze in a 1/3 there. Okay, oh, and then I always forget this, and then plus 1 at the end there. I left off my plus 1 from back there. So this would be my equation. Let's see if we can figure out what would be true about this equation, what things we know about it, and then we'll look at the graph and verify that all of those things worked. So the amplitude comes from the fact that this is y over 5. Okay, I'm just going to make a note over here what I'm looking at. I'm looking at the y over 5, which means my amplitude would be 1/5. And that also corresponds to this number right here. Okay, that's my amplitude. The period comes from the fact that I have a 3x there. Okay, so the period, this is saying though what's happening to the period in the original period is 2 pi. So it's really going to be 3 times 2 pi, which means my new period would be 6 pi. Phase shift would be the x minus 3 pi over 2 that I'm looking at. And so for my phase shift, I would say we're moving 3 pi over 2, and because this is subtraction, it would be to the left. Okay. Vertical shift would be that plus 1, and that means I'm moving 1 unit up. And then for frequency, frequency is kind of its own beast, but frequency, remember, is the reciprocal of the period. Okay, so my period was 6 pi, my frequency would be 1 over 6 pi.